you created 4 threads, but still you are getting only 2 times the speed up. It's not easy to do multi-core programming because the first thing that you, or by the way, it can also be called multi-threaded programming or multi-thread programming, whatever we can say. So multi-core programming, the first thing that it requires is that you think in terms of multiple activities being done inside your process. Right. So, for example, let me actually write it over here. For example, if I had a program which had it was doing 4 different things, right? So let me write it down. It was a word processing application. For example, it was doing the spell check in and it was also doing the an autosave in Microsoft Word. You may know about that. And similarly, there is something called, let's suppose it is like updating the display, right? Similarly, it is, let's say, grammar checking. These are 4 different activities. It was very easy for me to divide, these into 4 category, 4 activities because it was so natural to do that. My solution, the solution to this problem, word processing problem, was such a, you can say, natural kind of thing or such an organic kind of solution that it was already divided into 4 parts. So what do? I create 4 threads. I send all of these to, I send this to first thread, second thread, third thread, and fourth thread. So it will be very easy for me to, you know, make use of multi-threading in this scenario. This is, by the way, called uh, task parallelism. There is a name for this. This is called task parallelism. Okay, similarly, let me give you another example of a problem where I have I have to design a Photoshop application, right? Where the images that I'm getting are extremely large. These are from, people who have to work on images. These are very big images. Each image is, let's suppose, 1 million pixels into 1 million pixels, very large image. And you have to apply some kind of filter on it. For example, you have to remove noise from the image. There is a filter which removes noise from images, right? So, but if I send the complete 1 million by 1 million image to that filtering algorithm, it will take a lot of time. I have multiple CPUs installed in my system and I want to make use of that. I want to use multi-threaded application on that. What do you think I should do? I have a quad core computer. I have to remove the noise of an image of size 1 million by 1 million. This is single image. If I send the complete image to the algorithm which removes noise, it is going to take a lot of time. What should I do? Simply divide the image in, because I had quad core computer, simply, or probably I'm designing the Photoshop for 4 threads. So what I do, I send this image to thread 1 and this one to thread 2 and this one to thread 3 and this one to thread 4. All those 4 threads are running the same algorithm, so they will independently remove noise from all of these sub images, as we can call them. So this particular parallelism is called data parallelism, right? So this is also used quite a lot in practice. And there is another form of parallelism which is implicit to all of this discussion, and that is that, for example, you have an octa-core processor and you were running 100 applications which were all not, none of those were multi-threaded inherently, from design point of view. So the operating system would simply schedule 8 applications at the same time to the CPUs, right? So that is something which is a broader type of parallelism which will always be there. And you will see during multitasking all of your processes being run better on a multi core CPU as compared to a single core CPU. But a single application of yours can only benefit from multi-core computer only if you have written it using the threading technology. So the second most important concern while doing multi-threaded programming or multi-core programming is that you have to balance the load between threads. So if you have not successfully or efficiently balanced load between threads, your application will not get enough benefit from parallelism. Similarly, I gave the application of data splitting, like an image could be split into four parts. Similarly, data dependency, sometimes there could be a problem that when you applied the noise filtration thing on individual sub images, when you had to stitch the outputs together, there may be some boundary values or edges. They may have different values when they were used separately, and then when they were brought together and they were stitched together, and then you applied the algorithm on the stitched edge of both the sub images, the output would be different. So you will have that is called data dependency, that now you will have to run the algorithm again for the joining parts, and then you will have to wait, the sub images have to wait for the results of those boundary solutions to come, and then brought together with the original sub images. So similarly, testing and debugging of these multi-core programmings are very difficult, because there are so many permutations of different kinds of results between different threads, that it is really difficult to test and debug all of those different cases. As many number of threads you make, so many different numbers of cases arise that could be there for different types of combined outputs. So it's really difficult to debug such programs, and there can be bugs present in really mature applications as well. So this is what threading is all about. And so this is a single threaded application, and this is a multi-threaded application. Single threaded, you can see these are the parts like the code, data, files, registers, and stack. If I were to make two applications instead of one application, what would I do? I would make a copy of all of this process, right? This process is, I have copied this process into this process, right? So you can see that I have made the copies of code, data, and files over here. So it is taking much more memory. But instead, if I create threads, I am sharing the code, the data, and the files between all these threads. And the only thing that I had to make different was the registers and stack, because obviously these threads can see context switching between themselves, because they're running in parallel. They can be sent to different CPUs, so they must have their own stack and their own register set in order to work properly. So this is something which will have to be created in order to keep the context backed up into the memory. Otherwise, all those things, like the code, data, and files, they will be shared amongst all the threads. This is called data sharing. A word about speed up. So, how much speed up would you get from a program which was written using multi-threading? So, Amdahl's law is there for us to give us an answer on that. For example, I had a program in which 30% part was sequential, it was not parallel, and 70% part was written using multi-threading, like some thread library. So you can write it down as what, zero point 0.3, and you can write this as 0.7. Amdahl's law says that the speed up, and by the way, I'm saying that my this particular examples has four CPUs in the system, or in other words, we're assuming that we're creating four threads, right? So these four threads I am assuming to be four. There are n is equal to four. So the speed up using Amdahl's law has the formula 1 divided by the sequential part, which is 0.3, plus the parallel part, which is 0.7, divided by the number of CPUs that are available to us. So if you calculate it using calculator, you will see the value of S to be 2.1. You wrote a very good program with 70% parallel part, and you created four threads and sent them to four CPUs, but still you are getting only two times the speed up, right? So this is something that Amdahl wanted us to pay attention to, and that was that you should not expects too much from multi-threading, and if you want to, you should do something about it. Like you should write a program with 90% parallelism and not 70%,